So thank you for coming to my session today. And I'm excited to kind of meet all of you. And this is actually my first time at South by Southwest, so an exciting time. Actually, for us as a company, first time to show up here, which I think is a nice opportunity to kind of showcase what we're doing in the realm of digital design tools for the built environment, the physical world that we live in. I'm going to advance here. So the title of my deck here, let's see if this advances. Oh, could you advance the slide? Yes. Yeah, global infrastructure stress can open data, save it. And I'm here, my name is Greg Demchek. I'm also here with one of our users building a fusion reactor in southern France. And Linda's going to join me for a minute to look at how open data is being used to build one of the largest experimental energy projects going on in the world today, which is the ITER fusion reactor in France. So if you're not familiar with Bentley Systems, it's going to be a two-part presentation about Bentley Systems, what we're doing as a software vendor in this space, providing infrastructure software, engineering software, and also look at a practical example of how our software is being used to help construct and design this fusion reactor, which has huge potential to deliver clean energy. Again, my name is Greg Demchek. I'm our director of our digital innovation lab, what we call the iLab. And what I'd like to say is that we are prototyping the future today. And what that means is I work with a team of creative technologists, designers, front-end, back-end engineers, and we get hands-on with emerging technology to see how that technology might improve how our users, engineers, architects, contractors, builders, owners, can deliver better projects. So we play with things like IoT, robotics, AI, game engines, digital twins is sort of the subject that we're exploring. And I'll show you a little bit of the work that we've been doing here in the iLab today. But just to set that in context, so I run our innovation team looking at emerging technologies, but this is within the context of the larger company, Bentley Systems. So if you're not familiar with Bentley Systems, we are a software provider, not the car company. And we provide engineers with software that they need to design, construct, and operate core infrastructure around the world in order to deliver all of us like a better quality of life. And so practically speaking, that means our software is used basically in all these core sectors: transportation networks, water networks, energy networks, cities, and even subsurface and mining. So all the roads that we use every day, the bridges that we go over, the wastewater treatment facilities, all this kind of core infrastructure. We have tens of thousands of users across the globe that use our software on a daily basis to design and then construct these facilities. And this is a global activity. So these projects range from airports in China to roads and highways here in the US, to massive new rail networks in Indonesia, to also major rail network projects in the UK. And as we'll see, even the construction of fusion nuclear reactors in France. Specifically, what some of our users do is, I'll sort of set some context here. In the early stages of things, when you need to have an understanding of the state of your assets, our users can actually pop a drone, do photography of that drone, and then we can process that photography into what's called a photogrammetry reconstruction. And from that, you can then identify issues, detect cracks where that asset might have problems. So recently in Kentucky, after there was a massive set of floods, this engineering team went out, deployed drones, and captured the status of like 50 bridges in Kentucky in order to then produce a photogrammetry mesh and have an understanding of like what was the actual effect of that flood on the asset. And this is all now more or less automated through the use of drones, photography, photogrammetry, and machine learning. Another project recently opened here in California is one of the largest wastewater treatment facilities ever built in Sacramento. Used our software to do all the construction, the pre-construction planning, visualization in a digital way before they actually built it. And now that project is online. Other software that we have is actually the design and construction of power line systems. So this is an example in Africa where the software was used to design, implement, and then deploy new power grids into rural communities that didn't otherwise have electricity. So delivering electricity to remote locations. But on top of that, so that's the software. And so we've been developing this type of software, CAD, BIM, structural analysis software, the last 40 plus years. But now we're really at a point here where we're facing new pressures in society. And I'm going to talk a little bit about this, and this hopefully leads quite nicely into the potential of the fusion reaction idea. So we know that the population is continuing to expand and grow, and that's going to lead to increased urbanization. At the same time, we know that climate change is present with us on a daily basis, and we need to be thinking about resilience and also new forms of energy to support this increase in population and urbanization. And just to set that into context, it's predicted by 2050 that the population of the planet in cities will grow to 2.5 billion more people. So think about that's 100 more New York City scale Manhattans that has to be built and accommodate people. And right, what's underneath all the need for those people is core infrastructure, the energy, the water, the materials that will go into supporting those people in those cities. And by the way, another huge demand on the infrastructure is in fact our digital footprint. The increasing use of digital tools, AI in our smartphones is also going to be required, right? So the data centers that will need to be power these cities also puts a huge impact on the energy demands of a city. We also see a trend right now, about 50% of the population live in rural areas versus cities. That is looking to trend towards 68% by 2050. Where it's a vast majority of the population will be living in cities and will be consuming AI-powered interactions. So that all leads into this fact, right? As we increase our cities and the population grows and the demand on infrastructure grows, that does mean that we have to keep producing energy to power these cities. And we know that global temperatures are looking to go and exceed the 1.5 degrees C mark, right? And what is going to curtail that if we continue to grow at pace? So this is critical. And when we think about it as a software provider, we have to be thinking about providing solutions that aren't just being used to develop new forms of energy, renewable energy, but also to design systems that can be more resilient and more reliable in the face of these types of catastrophes. This is a photograph that was taken from Valencia a few months ago. This was a town that was completely wiped out due to flooding because that town wasn't designed for resiliency in the face of these types of floods. So that city's going through a massive reconstruction. On top of that, there's a huge issue within our specific industry, the engineering industry, that we have actually fewer and fewer engineers going through the education process in order to meet that demand to build all these new fantastic cities that are coming, whether we like it or not. And another issue that our users face, and I think this is common across many industries, is what's happened over the last 40 plus years, the development of CAD and BIM systems, is data operating in silos in file formats that don't always interoperate with one another, which leads to inefficiency. So just to put this into some context, some numbers, in the United States alone, we need an additional 400,000 engineers per year to keep up with that demand that's being predicted, the population demand, the demand on new infrastructure. We see similar numbers in Japan, in Germany, and also in the United Kingdom. So this is a global problem. It's not specific to the United States. There's actually just a lack of engineering skill set out there. The other issue that we've faced as an industry is this. Over the last 40 plus years, a huge ecosystem of software has developed in this space for CAD and BIM. And these are all different software vendors producing file formats that don't always interoperate with one another, which means you're sending files back and forth. And often that means that information is lost in that transmission. It's not always a lossless exchange of data. Of course, that leads to inefficiency, lack of communication, and complexity. I think this is really interesting. This was a paper that was put out in 2023 by a group of architects and engineers who kind of got fed up with this huge chaos of software that can't operate with one another. And they wrote themselves, the end user, open specification for what they expect the software of this new era to do. I think this is interesting. They said we need a universal data framework that all the software platforms can read from and write to, allowing for more transparent and efficient exchange of data between platforms and parties. So this is coming from the market, and we at Bentley Systems have decided to take that challenge really seriously and start investing in building cloud-native platforms that can, in fact, interoperate with all those other vendors, that allows for transparent access to the information, and that it can scale by moving everything into a cloud platform rather than just sending files back and forth. And so what we believe this will do is allow our engineers to spend more time on what they want to do, which is optimizing and improving designs, collaborating with one another in real time rather than waiting for information to go back and forth through files. And I think the idea here is that if we get all of this working together in a single connected environment, our end users, the engineers, the owners, the operators of these facilities can start to make better decisions. And so what we call here, our solution to this, if you haven't heard of this term, it's something we did not invent, it's a digital twin, right? So a digital twin is a way to represent a physical asset throughout its life cycle, from design, construction, all the way through operations, using a variety of digital tools, everything from laser scanning, photogrammetry, 3D modeling, IoT sensor information, anything that can be used to describe that physical thing using digital tools. And so this is really about creating a continuity of data through an infinity loop here, that information can go from design, construct, operations, and maintain, and continue throughout that process. So our solutions is, on the left-hand side, authoring applications for designing that are open-ended, that can work with many different file formats. There's no vendor lock-in in this case. Into construction, and on into asset operations and analytics through real-time sensor monitoring and understanding like the status of an actual asset. And underpinning all of this is we've developed an open-ended, open-source data platform for the exchange of information regardless of the vendor type, okay? And that's called our Cesium and iTwin platform. So the platform itself is designed to work with a wide range of information. Again, the digital twin, any type of data that can be used to describe an asset, we have to make API connectors to, so that you can bring in your content in or out, depending on your use case. So this is BIM, it's CAD, it's photogrammetry, it's laser scan, it's IoT. All this information can come together and be contextualized in an asset. So that's a bit of the vision. Now, I step back for a minute and think about platforms for a second. So I talked about our iTwin platform, but really it is a platform for communication ultimately. If we think about major evolutions in platforms, it's no surprise we've gone through the printing press was a platform producing text and sharing text at scale. The radio was a platform for communicating with audio. The television was a platform. Interactive CAD systems became a platform for communicating with the computer system and sharing that. And then with the digital twin and the internet, we can wrap the internet around all of that, and that produces a cloud-based operating system. And because we're working with 3D content, really this is where the idea of the metaverse or digital twin, a 3D experience, becomes a fundamental part of that experience, right? So it's the internet delivering 3D interactive graphics about an asset. And of course, now AI is able to interact with all this content. Text, audio, visual systems, it can even become an interactive system where you're an engineer having an interaction with agents in the context of this digital twin. So practically speaking, this is what Linton will get into in a second. In construction, we've also gone through a similar evolution just in the last 100 years, from Gantt charts, 2D graphics, and spreadsheets being communicated through radios, audio systems to the field, to now interactive 3D representations, that we call 4D representations, of the schedule linked to 3D geometry, producing computer animated graphics that can now be experienced in a multi-user interactive way, with mixed reality, with virtual reality, using game engines. So we call this infrastructure digital twins, because you can wrap all of that into the internet through a cloud solution. And then the question then becomes, now, as all of that data is existing in an open format, what does it mean if AI can now interact with that information and be part of the process? That's the questions we're starting to look at. Now, if I step back for a second and just think about open systems, open source systems, I think TensorFlow is a really nice one. This is a project that spun out of Google. If you're not familiar with TensorFlow, it's an open source machine learning algorithm that's really great at computer vision. So you've got companies like Airbnb, Spotify, and Airbus using that open source library to produce specific outcomes for computer vision for their specific users. So even like Spotify playlists are using TensorFlow. Airbus is taking satellite photography from space and doing insights on that with machine learning. We at Bentley Systems have also been part of this evolution, which is incredible, because now we can take crowdsourced photography. This is actually dash cam footage that come from delivery trucks, pull that video content out, train it on with machine learning to detect things like traffic signs, paint markings, traffic lights, and then geolocate that content back into a map, an open source map. And now you have suddenly a digital twin that's being generated by just leveraging the power of freely available content in the form of videos and photos, but training it with machine learning to then have an understanding of your asset. Before using this technology, you're talking about sending maintenance crews out there and manually doing an inspection and looking for issues. Now this can be more or less fully automatic. Another shift too in open standards is the use of 3D tiles. Similar to TensorFlow, this is an open source, open standard 3D tiling technique that allows any type of CAD data or point clouds or photogrammetry to be converted into an open source standard called 3D tiles, which can then be streamed into other platforms such as Unreal Engine, Unity, Omniverse from NVIDIA, or the web. And so this just completely opens up the door for interoperability and more rich experiences. If you're not familiar with 3D tiles, it's a very cool concept, actually. We're actually quite used to this with our phones, with maps, pinching and zooming, and the Google Maps kind of zooms in and out, and information loads automatically. It's the same concept, but now applied to 3D geometry. Okay, so we can zoom in from literally the scale of the entire planet Earth and zoom in down to like a construction detail, like a 3D bolt, and zoom back out. And the 3D tiling technique, the specification, allows for that dynamic loading and unloading of detail automatically. And it works across all those different platforms. Google, in fact, chose to use this format, cesium 3D tiles, as a way to get data that was locked in the Google Earth engine out into the public domain. So now with an API call, you can fetch tiles, these 3D tiles from Google, as an example of Vancouver, and get an entire photorealistic context of a city streamed into your application for geospatial context. And then you can build content on top of that. So you literally have access to the entire planet now as a backdrop to your projects. You can go in and find assets like this, like dams, cities. I think there's like hundreds and hundreds of cities that have been captured by Google with photogrammetry. Another example of a city. And then this is what it looks like when you kind of, okay, that's the backdrop. So you have an API call to go get all this geometry. So there you see, this is a light rail proposal in Australia, where the Google tiles are coming in for the geospatial context. The buildings are also streaming in with the 3D tiles. And then using Unreal Engine, this user has built a custom application where they add the animation, the characters, the weather patterns, and sort of build up that experience on top of this layers. So I think what's interesting here is just the multiple vectors of information that are able to stream into an app like this, Unreal Engine, from multiple different data points. So now we're using the power of like a game engine, but not for like storytelling, for like cinema, but for actual practical use cases for new projects coming online. Here's another example. This is a federation of 30 plus CAD files linked in through the platform, turned into 3D tiles automatically and streaming into an application. But then specific assets, in this case, the solar panel array, were also linked, those objects, to IoT sensors. So then the IoT feed of that sensor can be fed into that object as a data stream coming in, all with a runtime API. Oops. Yeah. So the way this works is basically it's your 3D data, whatever data that you have. Honestly, pretty much all formats are available today. It converts into these 3D tiles, which is an open specification, and then those tiles can be streamed in. That's also the new thing. It's not a file import. It's an API call, and then the tiles stream into your app, web app, or using one of these popular game engines. Okay, so now we're going to take a little bit of a break from all the conceptual stuff and get into how this is in active, real use at a project in France. And for that, I'm going to invite Linton Sutton to the stage. Thanks, Linton. Yay.
Hello. So my name's Linton. I'm director of Brigantium Engineering. We specialize in 4D planning and engineering studies. Our main client since 2019 has been the ITER project, so that's what I'm here to talk to you about today. So what is ITER? It's a nuclear fusion reactor. So just to give you a quick background on what nuclear fusion is, this is a little infographic here that explains the reaction that we're trying to replicate in the reactor. So at the top there you see deuterium on the left. It's an isotope of hydrogen. Tritium on the right. And what we're trying to do is fuse these nuclei together. And in that process, it gives off a neutron, which will escape at very high velocity, high energy, that will hit the walls of the reactor, generate heat, which we then use to heat up water, generate steam, turn a turbine, electricity. We'll come back to this again in a minute. One other thing I just want to mention before we move on. So I said it's deuterium and tritium, that's for the ITER reactor, but in theory, nuclear fusion could also work just with deuterium, so deuterium. And interestingly, deuterium, we find trace amounts in seawater. And this is a nice fact I like to give. In this amount of seawater, you in theory have enough deuterium to power the average household for an entire year. So if we get this right, it's a game changer. So here's a cross-section view of the reactor. You can kind of see it, but the little orange guy there, just below in the center, that's a 3D mannequin. Just sort of give you a sense of scale of this thing. It's a bit of a beast. So we're going to talk about it in a bit more detail now. So like I said, this is a cross-section. It will never actually be open like this. You have to kind of imagine that the whole thing will be closed. And this purple thing that we see in the middle is what we call a plasma. So what is a plasma? It's kind of a fourth state of matter. So you have solid, liquid, gas, and then after that you have plasma. Some kind of natural examples of plasma are things like lightning bolts, or the northern lights is a type of plasma. Also, like even neon lights is technically a plasma. So this fourth state of matter, it's if you think about it like a really hot kind of gas in a way. It's actually heated up to 150 million degrees Celsius. I don't know what that is in Fahrenheit for you guys, but it's very hot. It's about 10 times hotter than the core of the sun. Yeah, so pretty toasty in there. The next question is, how do we contain such a hot thing? There's no material on Earth that can withstand that kind of temperature. But it just so happens that the plasma is electrostatically charged. So what does that mean? It means that we can manipulate and shape this thing using magnets. So we have a huge array of magnets all around the reactor. I'll show you some more photos of that in a minute. But what it's the same technology that you have in an MRI machine, for example. And these magnets help to sort of shape and manipulate the plasma so that it doesn't touch the walls of the reactor. Another thing to mention is that inside the reactor, it's a vacuum, which also helps with not melting the machine. Here's a little close-up of the mannequin there, so you can see it a bit better. And there's a nice little video of the plasma. This is a real video. So, I mean, it looks a little bit like Northern Lights, actually, yeah. So, and inside this plasma is where that fusion occurs. And so here is one of those magnets that I talked about. So this one was manufactured in Japan. So manufactured in Japan, sent all the way over to southern France, where the project is located. And just to give you a kind of a sense of scale here, I mean, it doesn't look that big, but it's really heavy. And inside these magnets, there's actually, if you take there's 18 of these. And if you take the amount of copper filament that we've put into these magnets, there's enough copper filament to go around the Earth over 2 times. So yeah, it's quite a lot of material. And one of these magnets weighs about the same as a Boeing 747. I couldn't quite believe this, but I double-checked it, and it is true. They even put it on the ITER website. So yeah, I don't know how that's possible, but yeah, pretty heavy stuff. So these magnets, they get delivered, as we saw a second ago, they get delivered horizontally, get taken off a ship, and then somehow we need to put them upright. So this is how we do it. So this is actually what you can see here in this kind of tool that we call the upending tool. What it does is, yeah, we bring in the components horizontally and then sort of flip them up in the vertical position. So the cranes this is the assembly hall. The cranes do this kind of dance to put it upright. And so the component that we see here in the tool is actually part of the vacuum vessel. So here we see, this is a magnet now, being lifted. So once it's vertical, we put it into that machine behind it. So this is the machine that builds the machine, what we call the sector subassembly tool. So we lift it into these tools. And there you can see on the left there, one of the magnets. And on the right, this is a vacuum vessel sector. So every vacuum vessel sector will have 2 magnets sort of placed around it. So this is why I say it's a machine that builds the machine, because first we place the magnet, and then these huge rotating arms will then close to put those magnets sort of around the vessel. And then, yeah, we kind of we attach them together sort of temporarily, and then we lift the whole thing into the final resting place of the reactor. And so here you can see us lifting one of these sub-assemblies. And to use the aeroplane example again, this weighs about the same as 4 of those Boeing 747s. Yeah, pretty heavy stuff. So there we see it landing now into what we call the pit, the tokamak pit. Eventually there'll be 9 of these. So yeah, one sector module, but we're going to have 9 to complete that sort of donut-shaped reactor. And here we see, this is a photogrammetry model that me and my team made. So we flew around the pit with a drone, took loads of photos, and then we generated this pretty cool 3D model. Just wanted to share that with you. And just to give an idea of the scale of this thing. So in France, we like to say that this is the reactor will be equivalent to 3 Eiffel Towers. But I wanted to find something a little bit more culturally relevant for you guys. So don't know if you recognize that. That's Statue of Liberty. There's 100 on the screen. So yeah, the tokamak will be roughly equivalent to 100 Statue of Liberties, which I think is quite cool. So yeah.
That's cool. Thanks, Linton, for that. Now we're going to get into some of the details. What was interesting is at Bentley, we built this platform, which we call 4D, which is a simulation platform to link construction schedules with 3D models. And when I discovered that Linton was actually using the software to build this thing, that's when we started interacting, because it's like what you showed with all the installation. Like, how did you solve that with like the software ultimately to figure this thing out?
Yeah, I mean, it's, as you can imagine, it's a huge logistical challenge. So here we're seeing some footage of the work site. So we have over 4,000 people on site, components coming from across the globe. It's a very complex operation. Lots of different contractors to manage, lots of different teams. Here we see another example of a really heavy lift. But yeah, it needs to be a very tightly orchestrated operation. And so just relying on sort of traditional construction methods, Gantt charts and emails kind of wasn't really cutting it. So we're looking at ways to improve this process. And that's where we started working with 4D planning. So we use the Bentley product Synchro. And I'll just show you an example of 4D planning now. For those of you who haven't seen 4D planning before, this is kind of what it looks like. So at the very top, you can see just about the red marker there. That's the timeline. So you see sort of the focus point along the timeline. So time sort of moving from left to right there. A little bit bigger, you see the actual date that we're looking at. And so what we're looking at actually is a combination of the 3D models, so the engineering data, and the scheduling data. And we've tied them together in this 4D planning app, and now we can actually visualize the schedule. So it's a lot nicer to look at something like this. I mean, I imagine it probably makes sense to everybody in the audience looking at this, but if I show you the Gantt chart, I think we'll all be a bit confused. So, this is a really sort of game-changing communication tool. It's a great way for us to get all of the contractors, engineers, construction site supervisors kind of on board and really sharing a common vision of the path ahead. But now as we advance on the project, we're reaching a kind of a new problem. So just previously you saw that was quite a simple case. Now we're getting a bit more advanced in the tokamak assembly. I have to make more complex visualizations. So here you see there's a lot going on the screen. But I have to do this to be able to get all of the information across. So strangely, we're kind of ending up with the same issue that we were trying to solve, which is simplifying the visualization or the communication of these complex data sets. And so this is kind of where I reached out to Greg and we started working together. Sort of presented him with this challenge, saying, hey, can we do something better than this? And Greg told me that he was working with gaming engines at the time. So yeah. That
was the challenge, yeah. So this was the typical output of most of our users. Like the software itself combines the schedule, the BIM data, this open exchange, but then the output was usually videos. So back to files again. And Linton basically said, look, I'm creating all these videos, assembling all the videos. It looks incredible, but it's not real time, it's not interactive. And at that point, the iLab Innovation Lab, we started really experimenting with could we leverage Unreal Game Engine and some 3D tiling systems to sort of solve this problem. So maybe click. So Linton actually invited us to the site. We took the team down. We got access to these huge engineering models, the 4D models. We toured the site. We saw this thing in full scale. It's incredible. It's massive scale. And we started basically processing these models into these LOD tiles that we could then visualize first in VR, right? So we thought, what's the best way to kind of like get full interactivity is just moving your head around in the actual space. So you could get this actual sense of scale of being inside the reactor without having to physically be in the reactor, and kind of go a little bit beyond just looking at video to being fully immersed inside that 3D model. It also worked for like desktop applications because it's Unreal Engine. We could build apps for the desktop, but also we could stream that geometry into the VR headset. So that started out as an experiment. It's like a challenge, right? So innovation challenge. can you find a way to get these models running at high frame rate kind of automatically with the data stream rather than expensive file transfers or hiring a game agency to pull it off.
I think if I can just interject, I think interactivity is kind of the key. We noticed when you came down in 2021 that by having this sort of the ability to be able to interact with these data sets, the stakeholders were automatically more engaged with what they were looking at. So when they're more engaged, they're more likely to spend time thinking about what they're looking at. Then you get better feedback, better communication, and ultimately getting more value from these data sets. So I mean that was I think it's quite a game changer. So you want to have a look at what
next slide, and then this is the newest version. So what's interesting too, this is back to the open source idea. Open. When we first started this, we actually wrote a brand new proprietary file format to handle this use case, this dynamic LOD loading. But then we quickly realized we don't want to go down this path of making a new file format. So we started really using this cesium 3D tiles, and which is what you're seeing here. This is the latest version of the app running, and that's a recording of actual real-time gameplay, or navigation, we should say, with an Xbox controller moving through this super dense model, and it's a live connection. There's actually, in this case, we're no longer dealing with files at all. We're opening the app, making a connection with a permission, and then streaming this geometry into the app, in real time. And so you can see here too, we've got at the bottom, the translations here, but there's the 4D timeline is playing back also on the bottom. So you can scrub forward through the timeline camera to any point whenever you like. We do have this build running. If anyone wants to try it after the session, we've actually got the prototype up and running. You could actually fly through this reactor if you're so inclined. But yeah, that's kind of the idea, is like make it easy to interact with the content in a way that is intuitive and supports free-form exploration. And then the next slide. Then we came back. We kind of started with VR, then we went to desktop, and now we're kind of back to VR also with the 3D tiling system. So this is just streaming into a Quest 3 in this case. Again, you can get fully immersed in this reactor without having to go through any really extra steps. It's sort of, the technology has come down in cost and ease of use, that you can put a headset like this on and just with one click kind of be inside the reactor. And the same goes for the desktop application as well. There's Marcus on my team, flying through the torus. It's quite interesting. So,
just a closing comment, and I'll leave you finish the presentation. I think this is really important for the future of infrastructure, and also for projects like ITER. If we can improve the way that we construct these projects, improve efficiency, we can bring down the cost. So I think it's kind of essential for the future. A project like ITER, if we can reduce the cost by half, it starts to become more commercially viable, and that's what we want to ultimately achieve. So I think this is really important. Thank you, Greg.
Cool. Thanks, Linton. And Linton, you can just stay up here if you like for questions afterwards. We're almost to the end here. Yeah. Cool. So just to close this out, just to kind of hit these points about open data. So now I think we've got to the point where open data we know can work in interactive 3D systems. And I think that step to get into open formats running in the cloud with accessible APIs, obviously this is now the lead into AI. So everything you saw today was already quite an advancement just to get models running at frame rate at high scale. But now, can we imagine what happens when AI agents become part of that process, or the AI agent can learn from the past and actually start to do the automatic, 4D planning, what you could think of as generative planning scenarios. And also looking for defects, looking for issues, AI running around through the drone capture and just automatically finding defects and alerting the engineers to any potential problems. And so I also think about construction, start to imagine this world in which In fact, the model itself could have the instructions necessary for an AI to figure out how to actually build these things. Again, robot assembly, robot monitoring, and I think there's a huge possibility here that we'll see increasing use of robotics for both the construction phase, but also the monitoring of the status of the asset over time. So yeah, just to kind of close on this idea, like we just saw this like potential of fusion energy, which I think if you think about the issues I talked about earlier about massive growth in the cities and population growth and the rising temperature, we're going to need to start accelerating the development of renewable energy sources to power these cities, to power the data centers that are powering AI. And at the same time, continue to create resilient and reliable infrastructure through these tools, right? Make it easier for engineers to deliver these great projects. And I think ultimately we want to get to the point too where we're not just talking about efficiency and like optimization, but also know that we're building and constructing, empowering our users to really create that next generation of inspiring and beautiful infrastructure that we can all be proud of in the future. Yeah, so with that, that's our presentation. We've got about 10 minutes left if there's any questions. And if not, if anyone wants to stick around later, we've got time. I can have you take a spin around inside a nuclear fusion reactor if you want. So yeah, thank you for your attention today and for joining us here in South by Southwest. So I think if there is a question, if you have a question, we have a microphone. If not, I had to shut down the demo. I was prepared. I've got the Xbox controller ready to go, but I'd have to like launch that thing up. Questions about fusion, digital twins, interoperability.
Hey guys, thank you so much for the presentation. I would love to know more about open data and really the importance of open data for hugely complex projects like ITER. I've heard it described as the world's largest machines, and I can't imagine. So there's materials data, there's engineering data, there's all the visual data. So walk me through it and about the open platforms and how they can, and how projects like this one can benefit from them.
Yeah, sure. You want to talk about just the wide range of types of data?
I think ITER, for example, I don't think it's so much. I mean, it's huge. It's technically very complicated and it's a huge challenge, but I think we can do it. I think the real barrier for successful fusion projects is probably cost right now. So if we can, like I said, if we can improve the efficiency of construction, we can bring down the cost. And I don't know if we can do that without open data. I imagine with AI as well, I think we can accelerate progress even quicker. I don't know. I think there's a lot of possibilities, but I think I see open data playing a huge role in that. I mean, like we said, 4D planning is already a good example of open data. You're taking schedule data from one app. We're using Primavera P6, for example, and then we're taking engineering models from CATIA, and that's an example right there of open data. We're merging these two file formats and bringing them into this other software product, and it's a really powerful tool. So I think we need more of that.
Yeah. No, thanks for that, Linton. Yep.
Yeah, I have a question. So this is a cool project, by the way. It's a multi-year project. And as you're going through this project, the AI is also evolving. Every month we see new AI products come in and their capabilities is just exponential. How are you, is there a plan to integrate new upcoming AI into your future construction, or what are your thoughts on integrating the growth on AI and then affect the constructability of the project. Have you thought about that?
I'm not sure I really understood the question, honestly, but I don't know if there's any plans right now to integrate AI with ITER. Not that I'm aware of, but I mean, like I said, I think there's a place for it in the future for sure. I believe there are some other private projects that are toying with AI, so private nuclear fusion projects. So it looks like it's on the horizon for sure. I mean, personally, I spend a lot of time responding to technical emails, for example. So, I start to think, could we have an AI assistant that could help with just responding to emails, like technical emails? It will take me hours to kind of decipher and draft a response, but all of the technical data is already somewhere in some document management system. So could we have some kind of AI assistant that could go through and read all of these technical documents and draft a response? I mean, it would be a huge time saver. I don't know, maybe you've been in the same situation before where sometimes you're waiting on input from one of your colleagues, and maybe they're on holiday or they're busy with other stuff, and you could be waiting weeks for this kind of really important input. But same thing, all they're really doing is kind of regurgitating or reformatting something that already exists somewhere in your database. So I don't know, I think about that a lot. Also for my job for the 4D planning, I have to manually associate those 3D models with the schedule. So I mean, it requires me really understanding everything quite well in order to be able to do this job. So could we have AI playing a role in that? Sort of auto matching these models with the schedule. I mean, that would be a game changer too. Then we could, something that takes me maybe, I don't know, weeks could be done in a matter of days, or I don't know, hours. I mean, that would be a game changer too. After all, the best process is no process, as we know. So maybe AI could help with that. Yeah.
I have a question, maybe off base. I'm from the insurance industry, but so I see some of this and digital twins. When I see resiliency, I think peril. Is there any kind of concepts of like simulation to say stress on structure, construction, and what that would do to maybe some of the models that are being built in the framework?
Yeah, great question. Actually, I didn't cover that specifically in the deck, but we have a whole range of actually structural simulation software that'll do structural calculations on like steel, offshore wind farms, this type of thing, like really proper engineering simulation. We've also developed simulation tools for how like populations move through a facility to see how they react, like either egress from a stadium or if there's a fire. And this is all heavily trained data that simulates how people would react in an environment. So we've got that kind of simulation. We've got flood simulation also that will do full-blown computation on predicting like what would the effect of a flood on a piece of infrastructure be. And that speaks to resilience. If you could run that simulation like Valencia, imagine if you ran that sim ahead of time, then you could then intervene before the flood happens, and build up resilient infrastructure for that. So we have a whole host of different simulation tools that we offer. We also get into like subsurface too simulation, where just by taking like drill holes through the earth, using AI and machine learning, basically calculate and simulate what we believe is actually subterranean, without because you can't just excavate. You've got to kind of do sample points and then sort of generate what you think is down there. So yeah, absolutely. And the nice thing too is we can bring all of those back to the open data thing. A lot of these simulations operate in little silos, but now we can bring the results of the simulation in through, say, like an API, and even render that those animations in the game engine environment. So it's about making that like a connection of data. Yeah, great question. Thank you.
Hey, great talk. I love the nuclear reactor visualization. I just have a couple of questions about how that works. So, are there sensors on on it so that it like updates? Like if the ground shifts over time, are you operating with like the most up-to-date data?
So you're talking specifically about the models or about?
Yeah, so like if you're planning the model out and the model has this rendering and then over time something changes about the model, how does that get re-ingested into the model? Like is that an essential part of this or not necessarily?
Like plan versus actual?
Yeah.
Like you did the photogrammetry scan. Did you compare that again? Did you find like deviations, I guess, from what was planned versus what was actualized, or it's way too precise to get?
Yeah, I mean, we're really looking into the future more than sort of comparing our plan to the past. So, I mean, we haven't had to do that. I mean, I'm sure there is a use case for that, for progress tracking and things. But mostly we're forecasting, so it's very sort of forward-looking. So we haven't really had to do that yet, actually.
Okay, yeah, and then another question, just very tactical about the model itself, but I don't know enough to, when it comes to 3D models, you do the rendering, right? And sometimes they're just visual, and other times you can actually walk around in the model and there's physics and stuff like that. What kind of models are these, and is there like any advantage to having it where you can walk through the model or not?
Maybe you want to talk about the VR model?
Yeah. It's basic physics. It's colliders, which means if you go in there as like as an avatar, you'll walk on floors and you can fall off, and like fall off edges, that kind of thing. And when you're in VR, you get a real one-to-one scale, and you can literally walk around, and like that video we showed, like there were people ducking and moving underneath, like structural elements. So that works, and within like Unreal Engine, you had all sorts of particle effects, that type of thing. But I think what we're really trying to push here is like real-time interactive graphics using like millimeter grade engineering models, right? And we're not going through some kind of optimization pipeline or dumbing it down. It's like literally what those engineers are creating can get into this immersive, digital twin metaverse experience.
Yeah, it's one thing to see it on a screen, and it's another thing to kind of experience it in a VR headset. It's completely different. We were, I mean, in the example that we saw earlier where we're still wearing the masks, like Greg said, you see people ducking around, and we were looking at these models for years on the screen, but nobody ever really understood that you have such a like a space, like restricted space until you put the VR headset on. So yeah.
Yeah, hi, great presentation. You talked about leveraging open source, open data. Can you speak to like the level of effort that went into creating this 4D? Because I still imagine there's a lot of work, that has to be done to put all these pieces together. And do you think that, with a roadmap, that this can be more feasible for, shorter projects, just kind of your everyday, 1 to 2 year infrastructure projects?
Yeah, I mean, and actually, I sort of discovered that each was using the tool is used across the whole sector. It's for vertical construction, horizontal, smaller scale projects, and like these huge mega projects. What's interesting is like this, it's the same fundamental ingredients in all scenarios. It's 3D geometry, sometimes even just 2D line work, and then a schedule of tasks. And so it's about sequencing the work. And even like IKEA furniture or Legos, kind of like if you think about a Lego manual, it's a bit like what the software we developed, but like you're in full control. Like with a Lego manual, you get this sheet and it tells you what to do. That's kind of what Linton does. He kind of creates like the Lego manual for how to build this thing, and it's used across the board. Actually, almost every major sports stadium that's been built here in the U.S. the last 10 years all use this technology for all the construction simulation, the pre-construction planning, design review meetings. And so they'll literally do a whole digital rehearsal of like build the Lego pieces first, iron out the risk, and then deploy it to the field. So yeah, it works. It would work at any scale.
Cool. But for this project, like what was the level of effort that it took to, because you were saying you would physically map out the models to the geometry and the construction tasks. So do you have an estimate of the effort it all took, or?
I mean, we're constantly doing new studies, so it's not like you do the work once and it's done forever. Pretty much every week, we're doing like a new type of study, and it's not always the same. So we're not necessarily always focusing on the same area. But it depends. I mean, we do some really big studies. So one that we're about to deliver pretty soon, that's looking at kind of the next 5 years in pretty high detail, and that took my colleague, I don't know, the best part of a month probably. But I also do these other type of studies where we're just looking 3 months into the future, and that could take me, a matter of days. So yeah, it depends.
Cool. Thank you.
Thanks.
I just have a last question.
Yeah.
Can you just talk about how you use the model and the 4D element as part of a workflow? So for example, do you say like, hey everyone, today's day 25, here's a link to the time snap picture plus 3D model, and then like how do you track that work as you go, if at all?
Yeah, I think I probably glossed over that a little bit in the presentation, but that's an important point. I mean, like I said, it's like a forecast, like a weather forecast. You see one day that it's raining and you know to bring an umbrella. And it's the same with the construction forecast. If you see in the 4D visualization that there's a clash, for example, you need to do something about it. So, sometimes we just put in these little kind of boxes to represent like a working area. And if you have lots of boxes overlapping, you know that you're running out of space. It's one thing to see something working in a schedule, but this is kind of one of the limitations of scheduling, is that you can't really visualize the space or the what you're scheduling actually. So you kind of need to see it in 4D to understand how that translates into something a bit more sort of real world and something a bit more tangible. So I hope that answers your question. Yeah. It's visual. Yeah, we're looking at things like clashes between operations, or it could be something as simple as, okay, I can't install this component because there's something else in the way, and I need to move this first, and then we change something in the schedule, and then update it, and then it works. Hope
maybe just to comment on too, one of the things we're trying to focus, like what he produces with these meetings are these videos that get reviewed in like working sessions, and or the software itself, which is this very complex looking piece of interface, right? Like the design tool. And then what we were trying to do is like, wow, what if we could, oh, you got the model up and running. Oh, that's interesting. Here, you could like zoom in on this thing.
Go turn on the controller.
Going to launch or not, but that's what we're trying to show you if this thing will open or not. But then, like, well, imagine if in the meeting you could pass this device around, or people could zoom in and out with full interactivity rather than just looking at kind of the like the manual, right? Like the Lego manual. So I think that's what's new that we're trying to develop here is a fully interactive system. Oh.
How to zoom in?
Maybe this one here. Oh yeah, here we go. Okay, so this, thank you, Rahul, for firing this thing up. Now I'm just flying right into the reactor here with an Xbox controller. And so traditionally, Linton would take images out of the design software and then, share these with the team, maybe in Teams or in PowerPoint, or make a video. But now imagine if the whole team could just fly through this reactor, in real time, full control.
Yeah, that's right. So we would often have meetings, like a big team meeting, and I'd present my 4D presentation. And then, I'd write down the comments and the feedback from the team.
Like deep inside this thing.
So here we're inside the main vessel of the reactor. I'm just going to narrate what Greg is doing here. This is what it looks inside the reactor. So this is kind of an early stage, I would say, of the construction process. In the end, there'll be a lot more components sort of installed inside here. what we noticed is that, by virtue of having this thing being immersive, the stakeholders are generally more engaged with the content, which is good.
And then here we've mapped the timeline snap, so moments in time. And this is nothing really custom. It's literally just mapping an Xbox button. So then you can snap to specific moments in time and see that's the temporary construction. And that's the next kind of milestone. And so the graphics are loading according to the schedule, like just with a click of the button. And I think before, just to produce that video or set of stills might be an afternoon of work. Now it's always on, it's real time, lowering the barrier of entry. And the other thing that's cool about this, I think, which this is that open source data, this is the 3D tiling. This whole thing just opened up and it's all streaming from the server into the app based on the latest version of the file that Linton's working on, right? There's no, Rahul didn't open a file back there. Actually, just reopened the app and connected to the ITER project, and then the geometry streamed right in.
Yeah, I think this is a very good example of open data. We've got Primavera, CATIA, Synchro, Unreal Engine, all of these different softwares that are working together. And if you didn't have open data, this would not be possible.
Okay, cool. I think we're at 0.
Yeah.
So
thank you very much.
Amazing,
Thanks.
Real. Thank you for that. Thank you guys for all attending. I hope that was interesting, and appreciate your time. Thank you.